Right, hello there. In this video I'm going to cover empirical formula and molecular formula with you. Now this video is primarily aimed at GCSE students, but it's useful for A-level students as well. However, if you're doing A-level, please use the relative atomic masses, the AR values on your periodic table to 1 decimal place. At GCSE, most of the relative atomic masses are quoted as whole numbers. Now I'll start off with a definition of empirical formula and molecular formula for you. Then I'll show you what empirical formula actually means in a chemical context. I'll show you how to calculate an empirical formula. And finally, I'll show you how to convert an empirical formula to a molecular formula. So starting off with some definitions. The empirical formula is the simplest whole number ratio of atoms of each element in a compound. So if you did a calculation, you might get a 2 to 4 ratio of atoms of each element. Well, that's not a simplest ratio. It would be 1 to 2. You might get a ratio of, let's say, 1 to 2.5. Well, that's not a whole number ratio. You'd have to multiply each side by 2, and therefore you'd get a 2 to 5 ratio. Now, the molecular formula shows us the actual number of atoms of each element present in a molecule of a substance. Let's have a look at a couple of examples, and let's put this into practice. Now, the molecular formula of water, as we know, is H2O. So that means in each molecule of water, we've got 2 atoms of hydrogen joined to 1 atom of oxygen by covalent bonds. Now a 2 to 1 ratio, that is a whole number ratio, and that's in its simplest terms. So the empirical formula is exactly the same as H2O. Hydrogen peroxide, H2O2. Now that means in every molecule of hydrogen peroxide we've got 2 atoms of hydrogen and 2 atoms of oxygen. 2 to 2 ratio is not in its simplest terms. A 1 to 1 ratio would be. So the empirical formula is HO. Glucose, the molecular formula is C6H12O6. Now 6 to 12 to 6 is not a simplest ratio. Divide by 6 and we get our empirical formula as CH2O. Now propene is C3H6, an alkene. Just write that down. So C3H6, so 3 to 6, not a simplest ratio, but CH2 would be. So quite often the empirical formula and the molecular formula are the same, but the molecular formula will be a multiple of the empirical formula. Now, having a look at a typical exam question, we've got the masses of each element within a compound. Now, the first thing we've got to do when we calculate an empirical formula is work out the number of moles of each element by doing the mass divided by the AR value from the periodic table, which is the relative atomic mass. Now, it's a really good idea to scaffold your answer, so I'll do that now and show you what I mean. So I've written down what I already know. Now to work out the number of moles, as I said before, it's mass divided by the relative atomic mass. So 1.00 divided by 31, which is the relative atomic mass of phosphorus, and for fluorine, it's 1.84 divided by 19, which is the relative atomic mass of fluorine. Now let me work out those numbers of moles. Okay, so these are our numbers of moles. Now clearly we've got a ratio, but it's not a whole number ratio. Now to work out that, you would divide through by the smallest. So we divide that by 0.0323 and this one by 0.0323. Now clearly this is going to be 1, and in my calculator, if I get the number of moles of fluorine and divide it by the number of moles of phosphorus, I actually get 3.002. Well, that's close enough to 1 to 3, so therefore we can quote our empirical formula as P H3. Let's move on to another example. So this time we've got a compound with 13.5 grams of aluminium and 12.0 grams of oxygen. So like I did before, I'm going to scaffold my answer, so bear with me. So remember, to work out the numbers of moles, we get the mass and divide it by the AR. So these are my numbers of moles. Now, one thing I didn't mention earlier, in this stage, it's a really good idea to record your numbers of moles to 3 significant figures. Now we've got a 0.500 to 0.750 ratio, which if we divide through by the smallest, we get a 1 to 1.5 ratio. Now, we can't round that 1.5 up to 2 or down to 1. So what we've got to do is multiply each side by 2 to get rid of the decimal, and we get a 2 to 3 ratio. Therefore, the empirical formula of aluminium oxide is Al2O3. If we had a 1 to 1.01 ratio, we could round that 1.01 down to 1, and the empirical formula would be 1 to 1. But a 1.5, 1.25 or 1.75, or a ratio like that, you'd have to multiply each side by the same small whole number to get rid of the decimal. Now in an exam question, you might be given percentages. Now, if you're given percentages, deal with them in exactly the same way as you would if you'd got masses. Because for example, if you'd got 100 grams of this compound, it would contain 3.10 grams of hydrogen, 31.6 grams of phosphorus, and 65.3 grams of oxygen. So what I'm going to do, as I've done before, is draw some boxes and scaffold my answer. So as we've done before, we've just simply written down what the information in the question. So number of moles, mass divided by AR, the relative atomic mass. So hydrogen 3.10 divided by 1, phosphorus we divide by 31, and oxygen we divide by 16. So let me work out those numbers of moles now. Now if we divide through by the smallest, we get a 3 to 1 to 4 ratio, and therefore the empirical formula of this compound is H3PO4. Now, we can work out a molecular formula if we've got an empirical formula given for us, and we've also got an MR value, a relative formula mass. Now, this is how we do it. First thing you've got to do is to work out the relative formula mass of the empirical formula. So for example, for H2O, we've got 2 hydrogens and 1 oxygen, so the relative atomic masses are 1 for hydrogen, but there's 2 hydrogens, and 16 for oxygen, giving us 18. Now 18 divided by our MR here, which of course is 18, is 1. So this is a situation where the empirical formula and the molecular formula are the same as H2O. Now for CH2O, we've got an MR of 180. Now if I work out the MR of CH2O, so carbon's 12, and we've got 2 hydrogens, so plus 1 plus 1 plus 16 for the oxygen. That gives us 12, 13, 14, that gives us 30. So over here, if we get 180 divided by 30, we get 6. So we need to multiply the empirical formula through by 6. So rather than CH2O, it's C6H12O6. Now, for CH2 over here, if we work out the MR of this, so 12 plus 1 is 14. And then over here, if we get 42 divided by 14, we get 3. So the molecular formula, rather than CH2, is C3H6. Okay, so that's empirical formula and molecular formula, hopefully made simple. Thanks for listening.